Accurate positioning of heavy subassemblies and structures, such as cylinder cases of ship engines and large gearboxes of wind turbines, is a challenging task in heavy industry. Fine positioning and mating of these crane-hung objects requires special experience and is largely dependent on skilled labor. Workers standing near a crane-hung object, in this case a shaft, carefully adjust its position and orientation by directly and pushing and pulling it, while adjusting the height of the crane such that the object is aligned with the desired assembly reference, in this case a gearbox. Unfortunately, many heavy industries are experiencing a shortage of workers with the necessary expertise who can perform these tasks with high productivity. Further, utilizing inexperienced workers to perform these tasks can also be costly. If the shaft is incorrectly positioned, it may result in it becoming jammed within the hull, resulting in potential damage to the part or the disposal of the shaft in the structure. Therefore, there's a specific need for automating the process by which heavy objects can be manipulated, specifically focusing on precision alignment and mating processes of shafts within a gearbox. There are several aspects of this problem which need to be highlighted in order to understand the general scope of what my work accomplishes. The first key aspect is that we can observe that precision alignment and mating of a shaft within a gearbox is essentially a peg in a hole problem, which is a hallmark problem in the field of robotics, and it's been studied extensively, albeit using a much smaller peg, bringing me to my second key aspect, the size of the shaft. One of the features that sets this particular problem apart from the standard peg in a hole problem is the heavy mass of the shaft. As seen in the prior video, these shafts used in heavy industries can range from tens of kilograms into the hundreds. This is very important because it means that we cannot neglect the mass of the shaft in any subsequent analysis. A third key aspect of this problem is existing factory infrastructure, specifically the overhead gantry crane. Gantry cranes are very common in heavy industry, and it is to our advantage if we can utilize them. Now, there are some existing methods which could be adapted to solve this problem, each with their own set of challenges. The first is through utilizing standard industrial robots. While the peg-in-a-hole task is extremely common in robotics literature, it's primarily studied on a smaller scale. This research focuses on controlling all 6 degrees of freedom of the shaft to develop a variety of unique methods by which a peg can be inserted into a hole. There are industrial robots capable of manipulating extremely heavy loads, but these systems typically have large factory footprints and aren't easily transported, leaving them at a disadvantage in a constantly changing factory environment. The second is through use of cable-driven parallel robots, or CDPRs. CDPRs consist of cables that are attached to an object, in this case the shaft, and are controlled using winches. The winches control the lengths of the cables and can move the shaft through the workspace given the proper coordination of cable tensions. CDPRs have a high strength-to-weight ratio and are capable of manipulating very heavy loads. In robotics literature, these robots are seen as a solution to maneuver objects around a large area. Some of the more notable CDPRs are designed for use in manufacturing environments, such as the NIST RoboCrane and the CableBot. They're capable of positioning their end effector to perform tasks such as welding and pick-and-place operations. To the best of my knowledge, precision insertion tasks performed by large-scale CDPRs have not been studied. Similar to the industrial robot solution, if the goal is to control all degrees of freedom of the shaft, the footprint of the CDPR may be quite large due to the requirement that the cable tensions act in a particular direction. This brings me to a subspace of CDPRs known as cable-suspended parallel robots. Cable-suspended parallel robots, or CSPRs, are a subclass of CDPRs in which the end effector, in our case the shaft, is under-actuated, meaning that the CSPR isn't able to fully control all of the degrees of freedom of the shaft. In current robotics literature, CSPRs are typically studied to develop new path planning and trajectory following algorithms, such as seen with the SkyCam, and aren't typically used for tasks involving interaction with the environment, such as one might see in an assembly process. CSPRs have the same high strength-to-weight ratio as cable-driven robots, and with the right configuration, may take up less space than CDPRs. For example, consider the case where we reconfigure the CSPR as follows. By attaching the winches from the CSPR to the underside of a platform and then attaching that platform to the gantry crane, we can essentially mobilize the robot, eliminating the previous issue of having a large permanent footprint. Importantly, it also allows us to take advantage of the existing factory infrastructure, specifically the overhead gantry crane. Further, performing precision insertion tasks by controlling all degrees of freedom of the peg, as in the case with industrial robots and CDPRs, requires very precise force and/or position control. But by making the system under-actuated, we reveal an area within the robotics community that is yet to be fully explored. specifically performing precision insertion using an under-actuated cable-suspended robot. With that, I introduced the Winchbot system. The Winchbot is an under-actuated cable-suspended robot designed to manipulate a heavy shaft and to perform precision insertion of that shaft into a hole. The Winchbot consists of 3 winches, each attached to a linear actuator spaced 120 degrees apart. Each winch has its own cable that is connected to an instrumented gripper. The gripper is designed to grasp the peg and measure important parameters, such as the peg tilt using an IMU and the cable angles using encoders. The prototype developed in lab is capable of manipulating a 15-kilogram aluminum peg. A matching chamfered hole was machined for experimental validation, and the clearance between the peg and the hole is 120 micrometers. The static coefficient of friction between the peg and the hole is 0.67. To understand how we can use the Winchbot to accomplish a peg and hole assembly task, we must first understand the challenges associated with the entire insertion process. It's important to begin by defining what we mean by the term shaft, or peg, and the gearbox, or hole, for the purposes of this work. First, we define a peg as a cylinder without any external features, such as a keyway, with length L and diameter D. The center of mass of the peg is located at the geometric center of the cylinder. We assume the peg has an additional massless attachment at its top, which the cables can be affixed, denoted by the blue disc at the top of the peg. The cables are assumed to attach to the outer radius of this fixture, and the fixture has a radius of value rho, which does not necessarily have to equal the radius of the peg. Further, each cable is attached to the peg at angle phi. The hole is also defined to be a hollow cylinder whose diameter is denoted d sub h. The hole is a chamfer at the top surface of angle delta and width w. Further, we assume that the peg is positioned such that its center line lies within the hole plus the chamfer, basically stating the horizontal error between the center line of the hole and the center line of the peg, denoted as epsilon sub 0, lies inside the chamfer. It's also important to note that the peg can be lowered by one of 2 methods. The first is by lowering the platform attachment connected to the winches and the gantry crane. The amount of displacement of that platform attachment is denoted as delta y subsystem. This method may be used if maintaining a specific cable angle during insertion is very important. The second is by using the winches to keep the platform attachment at a fixed height and lowering the peg through the lengthening of the cables. Next, we must define the stages of peg insertion and identify the challenges associated with each stage. First is the point at which the peg first makes contact with the chamfered surface. As previously mentioned, it is assumed that we can position the peg such that it first touches down on the chamfered surface of the hole. The peg tilt, defined as theta sub 0, is assumed to be approximately 0, which is the first critical requirement for our peg insertion process to begin. Second is the chamfer crossing. The chamfer crossing occurs as the peg maintains contact with the hole chamfer and slides towards the center of the hole. During this process, the peg may experience a tilt, and the tilt at the end of the chamfer crossing is denoted theta sub f. In order for the peg to actually enter the hole at this point, the tilt at the end of the chamfer crossing must be less than or equal to this equation displayed on the screen, involving the diameter of the peg and the diameter of the hole. If the tilt of the peg exceeds this allowable tilt, the opposite end of the peg will get caught on the edge of the hole and physically cannot be inserted successfully. Next, we have one-point contact. During one-point contact, one edge of the peg is sliding along the edge of the hole at the end of the chamfer, and the other edge isn't touching. It's important to note that during the chamfer crossing in one-point contact, the position of the peg is still defined by the manipulator controlling it. As the peg is further inserted, the opposite edge of the peg comes into contact with the hole, beginning what is known as two-point contact. At this point, the position of the peg is determined based on two contact points. Any external forces acting on the peg may serve to increase the contact force acting between the peg and the hole, potentially leading to the peg jamming and unable to be inserted without correcting the forces. Further, if the depth at which two-point contact first occurs, L equals L star, is very shallow within the hole, the peg has the potential to wedge. To avoid this, we must be able to predict the depth at which two-point contact will occur. The difference between wedging and jamming will be elaborated on later in this talk, but for now, the main conclusions that we can draw are: we can minimize the chance of wedging by ensuring the depth of first two-point contact is sufficiently deep. If wedging does occur, we must be able to apply a correction method for the peg to be inserted successfully, and we can minimize the chance of jamming by ensuring that appropriate external forces are applied. From there, we must maintain these requirements until the peg is fully inserted into the hole and the insertion process is complete. This leads me to the two main contributions my work has within the robotics community. During the course of my research involving using an under-actuated cable-suspended robot, the Winchbot, to perform precision peg and hole insertion, I've determined the key conditions required for a cable-suspended peg to successfully cross the chamfered surface of a hole, and for the tilt of the peg and the depth of first two-point contact to be repeatably predicted. Further, I've determined the correct methods by which we can apply insertion forces to the peg once it's in two-point contact, so that jamming will not occur, as well as the required combinations of cable tensions that we can use to successfully remove the peg from a wedge state and reinsert it. I'll begin by discussing my work involving the successful chamfer crossing and repeatable prediction of the tilt and depth of two-point contact of a cable-suspended peg. To begin with, we must first look at what happens when the peg comes into contact with the hole. Three things can happen at the point of interest. The first is that the point of interest moves up the chamfer surface. The second is that the point of interest remains stationary on the chamfer surface. And the third is the point of interest begins to slide down the chamfered surface. Now, due to the fact that we are suspending our peg using cables who can only provide tension, the fact that our system is lowering the peg, the mass of the peg is pulling it downward, making it physically impossible for the peg to actually move up the chamfer surface. Now, if instead the point of interest does not move from the point at which it first makes contact with the hole, the mass of the peg will cause it to rotate clockwise about point A. Because the peg is not moving towards the center of the hole, it's considered an unsuccessful chamfer crossing. It's also important to note that in this situation, cable A, the cable on the left, is kept taut, while cable B goes slack. Similarly, for when the point of interest moves down the chamfer, point A slides down the chamfer surface, causing a counterclockwise rotation of the peg. Since the point of interest is moving down the chamfer surface of the hole, it's considered a successful chamfer crossing. And in this case, note that both cables stay taut. Now, this leads me to an important point that differentiates this method of peg insertion from traditional methods. During peg insertion with the traditional robot, if the stiffness and motion of the robot gripper isn't carefully controlled, then the peg in the hole may experience very large reaction forces should the peg fail the chamfer crossing. Essentially, the robot may push the peg harder into the chamfer because the peg is unable to translate the applied force into a motion. If this happens, the peg and hole may be damaged. On the other hand, we can exploit the unidirectional property of cables in that cables can only provide tension forces, meaning that when the peg touches the chamfer and fails the chamfer crossing, the cables do not push the peg harder against the hole, specifically because one of the cables goes slack. And in fact, the only reaction force the peg experiences comes from the mass of the peg pulling it downward. So now we need to determine the conditions that result in either a successful or unsuccessful chamfer crossing. We can do this using two methods. By looking at the balance of forces and moments between the peg and the hole, and looking at the kinematics and motion of the peg due to the cables. First, we'll look at the static force balance between the peg and the hole. First, we assume we have the situation that the peg first touches down on the chamfer. The force vectors from the mass of the peg, the tension in the cable, and the reaction force from the chamfer surface all intersect at a single point. This results in the peg sticking to the chamfer and cable B going slack. It's important to note that the friction cone of the reaction force limits the range for where these three forces can meet to the line AB. We can find the attachment angles of cable A that avoid intersecting the line AB, thus eliminating the possibility of the peg sticking on the chamfer due to friction. We see in the figure that the region of cables that intersect the line AB is denoted in red. Therefore, the regions in which sticking cannot occur are in green, providing upper and lower bounds for the cable mounting angle, phi, so that it is guaranteed not to stick on the chamfer. The range of cables is defined in the displayed expression. This expression takes into account the dimensions of the peg and the coefficient of friction between the peg and the hole, and provides the boundaries for allowable cable angles to avoid sticking. Depending on the geometry of the peg, certain cable angles are more likely to avoid the sticking condition. For shorter pegs, larger cable angles are more likely to avoid the sticking region, while for long pegs, smaller cable angles are more likely to avoid that region. Next, we look at the kinematics for a peg suspended by cables. The only way for both cables to remain taut during the chamfer crossing while also in contact with the chamfer is for the peg to move based on kinematics. In fact, by treating the taut cables as rigid links, they form a 4-bar linkage with the peg cable attachment and the base. 4-bar linkages have specific motions that are available to them based on the lengths of each link. We can determine the motions of the peg based on the allowable motions of the 4-bar linkage and find the kinematic trajectory for the tip of the peg that will be in contact with the chamfer. These trajectories are determined based on the lengths of the cables, and the motion that the tip of the peg will undergo is determined by the location of the instantaneous center of rotation, or COR. For a 4-bar linkage, the COR for the blue and green links is a point common to the two links, which experiences the same instantaneous velocity. Essentially, the 4-bar linkage appears to be rotating about this point. The trajectory for the center of mass and for the point of interest can be determined based on how the peg rotates about the COR. It can be seen that varying the location of the COR changes the trajectories of both the center of mass and the point of interest. We're able to use the trajectory of the point of interest to determine if the peg will be able to successfully slide down the chamfer using a simulation technique I'll describe next. First, we begin with a chosen peg and cable configuration. The point of interest of the peg has a known kinematic trajectory due to the center of rotation and is at the point where it's only just touching down on the chamfer. We then displace the system downward by a fraction of a millimeter. Now, because we are assuming the peg moves kinematically, it must follow the specified trajectory, which appears as a straight line when viewed up close. Therefore, the new actual location of the point of interest is the point at which the kinematic trajectory coincides with the chamfer surface. Once we have found the point of interest, our peg assumes that configuration, and we can repeat the displacement intersection simulation. There may be some cases in which the trajectory of the point of interest wants the peg to move up the chamfer. As I previously mentioned, one of the big assumptions with this method is that both cables are taut and treated as rigid links. However, a true rigid link 4-bar linkage is able to apply compressive loads, making it possible for a rigid link mechanism to potentially move up the chamfer. However, since the cables are not able to apply those loads, the peg essentially remains stationary on the chamfer, but it tips over, causing the right cable to go slack and the chamfer crossing to fail. I'd like to emphasize the phrase stationary. For the remainder of this section, when I refer to the peg being stationary on the chamfer, it's due to the result of kinematics, whereas sticking, discussed previously, is a result of the friction interaction and force balance between the peg, hole, and cable tension. The peg may also move down the chamfer, which results in a successful chamfer crossing. In this case, both cables remain taut, and the desired trajectory requires both cables and rigid links to remain in tension, meaning that the 4-bar linkage model is applicable during the entire chamfer crossing. Similarly to the sticking phenomena, due to friction, we can find ranges of cable angles that will result in a desirable chamfer crossing trajectory. First, when the cable angles are small, the trajectory of the point of interest is directed straight towards the center of the hole. Second, when the cable angles result in the center of rotation being near the tip of the peg, the trajectory of the point of interest results in the peg remaining stationary on the chamfer surface and tipping over, thus failing the chamfer crossing. And third, when the cable angles are very large, basically 90 degrees, there may be some vertical motion at the point of interest trajectory. However, this is tempered by the lowering of the peg and with the overall larger horizontal movement of the point of interest, allowing the peg to successfully cross the chamfer with both cables remaining taut. These also vary to some extent based on the ratio of length to width of the peg, but the general case is shown here. We can use the simulation to estimate the full trajectory of the peg during the chamfer crossing through 1-point contact and up to 2-point contact. From the previous methods I've discussed, we're able to develop guidelines that ensure a successful chamfer crossing. The cable angles and the coefficient of friction between the hole and the peg are the two main design parameters. Previously, I showed the conditions that would potentially allow the peg to stick to the hole. This provided an upper bound and a lower bound for the sticking region. I also showed the 4-bar linkage kinematics that would result in the peg remaining stationary on the chamfer. Any combination of cable angles and coefficient of friction that falls within either the stationary region or the sticking region has the potential for an unsuccessful chamfer crossing, denoted as not allowable regions. Therefore, when setting up the Winchbot to perform peg insertion, this graph should be taken into account to ensure a successful chamfer crossing. It's important to note that this graph varies depending on the geometry of the peg. This means that it's important to understand how the allowable and not allowable regions change as we vary the length and diameter of the peg and the angle of the chamfer. First, we look at varying the length of the peg. As we see, as the length of the peg increases, the not allowable region decreases for both the sticking and stationary regions. The not allowable region converges so that it only contains very steep cable angles. Conversely, as we increase the diameter of the peg, the not allowable region increases. In fact, a successful chamfer crossing is virtually impossible for wide pegs with larger coefficients of friction. Finally, as the chamfer angle is increased in steepness, the not allowable region decreases, which is a rather intuitive result, as the chamfer surface helps guide the peg toward the center of the hole. We can also see how any rotational misalignment between the peg and the hole affects the depth of first two-point contact. This assumes that the peg crosses the chamfer normally, but the hole is mounted at a small angle. If the tilt of the hole is such that it is more in line with the trajectory of the peg, we can see that the depth of two-point contact is actually deeper than it would be if the hole wasn't tilted. On the other hand, if the tilt of the hole is opposite that of the peg during one-point contact, the depth of the first two-point contact is smaller. It's also important to note that the peg, when suspended by large cable angles, is particularly sensitive to the tilt of the hole, and the depth of two-point contact varies drastically. Additionally, while transporting the peg using the Winchbot and gantry cranes, we don't want the peg to swing wildly throughout the factory, nor do we want it to bounce off the chamfer surface when making first contact. We can tune the type of sway the peg experiences by changing the cable mounting angles. When the cable angles are very large, When the cable angles are very large, the peg sways with a very low frequency and experiences very little damping, meaning it will sway for a long time. When the cable angles are small, the peg sways with a high frequency, allowing for the motion to dampen out quite quickly. And when the cables are tuned to a sweet spot, we can actually cancel out almost all of the sway immediately, and you can clearly see the peg's resistance to external disturbances. I manufactured a temporary 2D experimental setup for performing experimental validation for this work, which I'll describe next. First, I conducted an experiment in which the coefficient of friction was varied between the peg and the hole using different types of tape. Insertion was then attempted with the peg. For that particular combination of coefficient of friction and cable angles, if the peg either stuck or was stationary on the chamfer, we marked the location with an X. If the peg slid down the chamfer, it was marked with a circle. As you can see, the peg being stationary or sticking only occurred within the not allowable regions, and sliding occurred outside that region. Next, an experiment was conducted to verify that the 4-bar linkage kinematics and trajectory simulation I discussed previously could accurately predict the tilt of the peg at the end of the chamfer crossing. This is of critical importance because if the tilt of the peg is too large at the end of the chamfer crossing, it will be unable to enter the hole successfully. In this figure, the black region depicts the predicted sticking and stationary region for the peg used for these experiments. The solid lines refer to predicted angles at the end of the chamfer crossing using the displacement simulation. Each dot represents the average of 5 experimental trials physically performed for that particular cable angle. Each color represents a particular amount of initial horizontal displacement between the peg and the hole on first contact. As you can see, the measured values of peg tilt follow the predicted values very closely for every tested cable angle and for all 3 tested horizontal displacement errors, meaning that the 4-bar linkage simulation is a valid method to predict the peg tilt and ensure the peg can enter the hole. Next, an experiment was conducted to verify that the 4-bar linkage kinematics and trajectory simulation can accurately predict the depth of first two-point contact. This is of critical importance because if the depth of first two-point contact is too shallow within the hole, wedging may occur, and we will have to attempt reinsertion. As with the previous experiment, we have the sticking and stationary region in black, the predicted depth in solid lines, and the measured data as circles, with each color representing a measured amount of horizontal error between the peg and the hole. As you can see, the measured values of two-point contact follow the predicted values very well for all 3 tested horizontal displacements, meaning that the 4-bar linkage simulation is a valid method to predict the depth of first two-point contact. It can be seen that the large discrepancies measured between the measured data and the predicted values occur with large cable angles greater than 85 degrees. Based on the previous parameter study in which the angle of the hole was varied, it's believed that these large errors can be attributed to small amounts of angular misalignment between the peg and the hole. Overall, the model can predict the experimental results satisfactorily. So in summary, we can use the theory I've developed and verified to perform a series of design steps for choosing the cable angles at which the peg should be mounted such that it can successfully cross the chamfer and enter the hole and reach two-point contact at a sufficient depth to avoid wedging. First, the geometry of the peg and the hole are defined based on the parts to be assembled. Then, the sticking and stationary regions are determined to eliminate potential cable mounting angles that will not result in a successful chamfer crossing. Of the allowable cable angles, we can then eliminate those which result in a peg tilt too large for the peg to enter the hole. And finally, we can choose the desired cable mounting angle based on the remaining angles that result in the deepest predicted depth of first two-point contact. This brings me to my next contribution, the analysis and control strategy for ensuring jam-free and wedge-tolerant peg insertion. As I previously stated, my first main contribution focused on the first stages of insertion, from first contact to the point of first two-point contact. Once two-point contact has been made, we must ensure that it can be fully inserted without jamming and with the ability to correct for wedging should it occur. When a peg makes contact within a hole, a reaction force is generated as well as a frictional component associated with that reaction force. The magnitude of the reaction forces is determined by the applied forces and moments, Fx, Fz, and My. By simply observing the sum of the forces along the z-axis, it's obvious that if the vertical friction components, μF1, μF2, are larger than the applied vertical insertion force, Fz, the peg will not move downward into the hole. This is known as jamming. The magnitude of the reaction forces F1, F2 is determined by the magnitude of the lateral force and moment, Fx and My. By minimizing Fx and My, we can ensure the reaction forces F1, F2 and thus the friction forces μF1, μF2 are small enough so that the vertical insertion force is able to insert the peg. Now, traditionally, nearly all of the prior art found for robotic peg and hole insertion is capable of actively controlling the amount of force in the vertical and lateral directions through careful control, either by using elastic structures like the remote center of compliance pioneered by Whitney, or using active methods like active force control. These methods require careful tuning so that the robot does not apply ill-proportioned forces. In our case, our cables provide the forces required to balance the mass of the peg so that it can be lowered into the hole. Because the cables cannot provide a pushing force, the mass of the peg is actually providing the insertion force, and the position is constrained by the cables. We must then ensure that the cable tensions applied to the peg do not cause jamming. First, we can write out the sum of the forces and moments. Then, by rearranging the equations, we form what is known as the quasi-static jamming equation, originally developed by Simunovic and Whitney. The equal sign in the equation can be replaced with a less than sign to account for non-quasi-static sliding, meaning that the peg is falling into the hole. If this equation is satisfied, it's guaranteed that the peg will not jam. Now, by taking a closer look at this equation, we notice two important things. The first is that this equation is more likely to be satisfied by minimizing the lateral force and moment, Fx and My. The second is that as the peg is inserted deeper into the hole, the peg is more resistant to jamming through the application of these lateral forces. After deriving the jamming equation using the peg and hole contact forces, we can solve for the forces applied to the peg by the cables and the peg mass that are to be substituted into the jamming equation. After performing the substitution, we reveal the jamming equation for a peg suspended by two cables. If the term on the left-hand side of the inequality is less than 1, the peg will not jam in the hole during insertion. We can also see that if this term is minimized by minimizing the difference between the two cable tensions. However, we must also determine the jamming equation for a peg suspended by 3 cables in a 3-dimensional space, so we can apply it directly to a factory setting. Let me begin by defining the geometry of the peg in the 3D case. The coordinate system for the peg, axes u, v, w, is defined about the radial center of the bottom of the peg. The peg has length L and radius r. Similar to the 2D case, we assume we have a massless cable attachment fixture attached to the top of the peg with radius rho. The cables are attached, spaced 120 degrees apart. The peg has mass m located at the geometric center of the peg, where LCOM equals 1/2 the peg length. The cables are defined as cables 1, 2, and 3, each with its own magnitude of tension, T1, T2, and T3 respectively. Now, the cable tensions can be divided into several components based on the cable attachment angles. Phi is defined as the angle between the cable tension vector and the UV plane. Xi is defined as the angle between the cable tension vector and the vector along which that specific cable is attached that acts through the radial center of the peg, also known as the twist angle. These angles can be used to break down the cable tension into its subsequent components. It's important to note that all three cables have this vector breakdown. However, they've been grayed out to simplify the figure. Now that we've identified the geometry of the 3D peg, we can translate the previously found jamming equation from the 2D case to the 3D case. Here's where we come into our first challenge. While the 2D case assumes we are acting in a single plane and the attached cables also act in that plane, the 3D cables may not necessarily act within a plane as nicely. Now allow me to elaborate. We assume that the peg makes contact with the hole at points C1 and C2. In the 3D case, we assume the peg also makes contact with the hole at these 2 points. These points define a plane, which directly corresponds to what we see in the 2D case, but without the cables. We can then define this plane with respect to the peg's UVW coordinate system by defining the angle psi. The angle psi is defined as the rotation of the contact plane about the W axis. Taking this one step further, we can define a new set of axes, x, y, z, that act within the contact plane. Since we have defined these new axes to act within the contact plane, if we were to view the 3D system normal to this plane, we would see the same figures in the 2D case. However, there may not be an explicit 1-to-1 ratio between the 3 cables in the 3D case and the 2 cables in the 2D case. Therefore, we need to find a transformation that will allow us to utilize the previously found jamming equation for the 2D case, but with the 3D system. First, we begin by defining the components of tension acting within the peg's UVW coordinate system. Each cable tension has a component that acts along the U-axis, the V-axis, and the W-axis, and is defined by 2 angles, phi and psi, which are the cable mounting angles and twist angles. Next, we must make an assumption about the twist angle. As they are drawn, each twist angle is defined to be positive such that it would provide a clockwise rotation about the W-axis of the peg. However, when the peg is suspended in static equilibrium, there is no active rotation, meaning that the twist forces from the cables must balance. One such example of this is displayed here. As you can see, at least one of the twist angles must act counterclockwise to balance the other twist forces. Further, in the cases where the peg is centered between the winches, the twist angle may be quite small. These 2 features allow us for making the simplification that the twist components are all approximately 0. This leads to final expressions for the components for each cable tension. These tension components can be defined to find the sum of the forces and moments acting about each of the peg's axes. Now, assuming the peg has made 2-point contact with the hole, we form the contact plane and define the angle psi. We can then use a standard rotation matrix to transform the forces that the cables apply in the UVW axis to the planar XYZ axis. For the forces, the result is the following, and for the moments, we have this. We can then substitute the required forces and moments into the 2D jamming equation discussed previously. Performing this substitution reveals the planar jamming equation for a peg suspended by 3 cables, which was one of the main goals needed to achieve jam-free cable-suspended peg insertion. Now that this equation has been derived, a strategy must be developed for ensuring this inequality is met during insertion. The first point of the strategy is to notice that all of the terms on the left-hand side of the jamming equation are dependent on the contact angle psi. While the peg is in motion and is being actively inserted, it's very difficult to measure the actual value of this angle. Therefore, any control strategy we implement should be valid for any contact angle. The second point is to note that we are also assuming jamming happens within a 2-dimensional plane. However, the cables act in 3 dimensions, resulting in in-plane forces and moments and out-of-plane forces and moments. To ensure that the peg remains in a constant planar contact, we must aim to minimize the out-of-plane forces and moments. First, we rewrite the jamming equation and the out-of-plane forces and moments for clarity. By observing these, one thing that immediately springs to the surface are the repeated terms. We can see the terms A1 through A4 are repeated in the expressions for Fy and Mx. Therefore, we can further simplify these expressions. Now, the jamming equation and the expressions for the out-of-plane forces and moments are all functions of the terms A1 through A6. As I previously stated, we will not be able to actively measure the contact angle psi. Therefore, the only way to guarantee that the jamming equation is satisfied and the out-of-plane forces and moments are minimized, regardless of contact angle, is to make sure that the terms A1 through A6 are all equal to 0. We can then use the previously defined expressions for the components of cable tension and expand the terms A1 through A6 as shown. Now, as I mentioned before, our goal is to find a way to simultaneously make all of these terms equal to 0. We notice that the terms A1 and A3 are equal to 0 when the vertical components of cable tension are satisfied. We also notice the terms A2, A4, A5, and A6 are equal to 0 when the planar components of tension are balanced. This presents two conflicting conditions and actually makes our system overdetermined, meaning that it's impossible to satisfy both simultaneously. Therefore, we must choose which condition to satisfy, either balancing the vertical components or balancing the planar components. Which condition we choose to satisfy depends on the geometric properties of the peg, specifically the length and the radius and the cable attachment radius. It also depends on the angle at which the cables are mounted. If the peg has a large length to radius ratio, the horizontal components typically have a large impact on the jamming equation. And if the jamming equation is satisfied due to the length of the peg acting as a moment arm. If the cable angles are shallow to mid-range, the UV planar components of tension are also larger than the vertical components, meaning that for these two cases, the UV planar tension components should be balanced. However, if the cable angles are large, the UV planar components of force are very small, making it more prudent to balance the vertical forces instead. I completed experiments using the 3D Winchbot prototype as previously presented. This prototype manipulates a 15 kilogram peg with 120 microns of clearance. This first experiment depicts the peg being inserted and extracted without any sort of controller. You'll notice on the graph to the left that the top graph displays the tension in each cable, and you can see immediately that the three cable tensions vary drastically from each other. On the second graph, you will see the depth of the peg within the hole as it is inserted and extracted. In the case of peg insertion, because the cables are constantly increasing in length, they will begin to slack if the peg is not moving within the hole. If the peg is temporarily jammed, the cables begin to slack, and at some point, the mass of the peg acting as the insertion force will cause the peg to accelerate into the hole briefly. This type of motion is what I'm calling stick-slip behavior. And on the bottom graph, you will notice the jamming inequality. During insertion, if the jamming inequality is greater than 1, the peg is jammed. And for extraction, if the inequality is less than 1, the peg is jammed. If this inequality equals to 1, the process is quasi-static for both insertion and extraction. So here you'll notice the rattling noise and the jittering behavior, which is indicative of stick-slip. You can hear the creaking of the peg within the hole as the forces are causing jamming to happen. So obviously not the most desirable of behavior. However, when we use the controller, I can demonstrate the effectiveness of the proposed control strategy in which we balance the planar forces of cable tensions. So we notice in the top graph on the left that the tension components are largely equalized, resulting in a smooth insertion and extraction that satisfy the jamming inequality during the entire insertion process. So you'll notice a much quieter and smoother insertion and extraction. Sorry. Sorry for the pauses, but it extracted successfully. We can watch the video later if we have enough time and if you want. So now that jamming has been addressed, we must account for another phenomena, wedging. When the peg is inserted into the hole, we assume it makes two-point contact at a specific depth. If that depth is particularly shallow, the reaction forces from the peg hole contact may point directly at each other within their respective friction cones, creating a force closure. This assumes that the insertion force causes some energy to be stored between the peg hole contact points through elastic deformation. Upon release of the applied insertion force, the elastic energy remains, causing the wedge. For a small peg tilt and small clearance between the peg and the hole, there is a corresponding smallest peg tilt and largest depth at which wedging can occur, both of which are proportional to the coefficient of friction between the peg and the hole. In this case, the wedge can theoretically resist any additional applied insertion forces. It may be possible to remove the peg from the wedge state by applying a very large load. However, this may cause damage to the part at the contact points. The only real way to correct for wedging is to remove the peg from the hole, reposition the peg, and attempt reinsertion, such that the first 2-point contact is deeper within the hole. So in order to implement this in the Winchbot system, we must determine the appropriate conditions that will allow us to break the wedge state using cables. Wedging can be broken in 2 ways, by applying a pulling force at point C1 or providing a moment at point C2. The wedging forces in this case are defined as N1 and N2. To break the wedge at point C1, we must apply a force, F sub A, at point A so that the reaction force, R1, lies outside the friction cone. This occurs when the following inequality is met. If the left-hand side of the equation is greater than the right-hand side, the wedge will be broken. In this case, it requires the coordinated effort of the vertical components of cable tension. Balancing the perpendicular forces, so the planar forces, means less overall tension is required to break the wedge. We can also break the wedge by applying a moment at point C2. In this strategy, a moment applies force F sub m at point A so that the reaction force, R2, lies outside the friction cone. This occurs when the following inequality is met. Once again, if the left-hand side of the inequality is greater than the right-hand side, the wedge will be broken. In this case, having a larger difference in cable tension will actually help break the wedge. This strategy chosen depends on the cable angles, phi. If the cable angles are relatively steep, the vertical components are large, meaning that it'll be easier to have this peg slide at point A, strategy 1. This has the added bonus of utilizing the pulling capacity of all of the winches. If the cable angles are relatively shallow, the planar cosine components are large, thus it's easier to create the required moment about point B. This may require significant torque from a single winch. In both cases, it's important to note that the amount of cable tension required to break the wedge is proportional to the wedging force, which is a function of the elastic deformation between the peg and the hole. We don't necessarily need to know the exact value of the wedging force because of this proportionality. Essentially, we can continue to increase the applied tensions with the appropriate balance until the wedge is broken. These equations can be modified to perform wedge breaking in the 3-dimensional case. You may notice a repeat of the A2 through A4 terms we saw previously during jamming. When the peg is wedged, it is not moving, allowing for the measurement of the contact angle psi, meaning that we can solve for the correct proportions of cable tensions required to break the wedge using either strategy. Now that we've determined how to break the wedge, I can introduce you to the full wedge correction strategy implemented on the Winchbot system. First, we must detect that a wedge has occurred. Once the peg is wedged within the hole, the wedge must be detected. The simplest method for detecting the wedge is to monitor the cable tension. If all the cable tensions are simultaneously below a certain threshold, it can be said that the peg is wedged. Also, during the wedge, the IMU can be used to determine the steady-state value of the peg contact angle, psi. After the wedge is detected, the slack in each cable must be removed before the wedge is broken. The tension in each cable is increased by tightening the cables until the tension in each cable is approximately equal to the value it had before the peg became wedged. Once cable slack has been eliminated, a wedge breaking strategy can be employed. As previously stated, choosing the strategy is dependent on the hardware and system configuration. If the cable angles are relatively steep, it will be easier to break the wedge through utilizing strategy 1, where we pull with all of the cables vertically. If the cable angles are shallow, it might be easier to create a moment about a point using a single winch. After the wedge has been broken, we must detect it immediately. Otherwise, the peg may accidentally be removed from the hole. To detect if the wedge has been broken, we can note a spike in acceleration of the peg and in the tension of the cables. However, the amount of tension required to break the wedge and the amount of acceleration the peg experiences may vary depending on the severity of the wedge and the speed at which the cables apply the wedge breaking tensions. In my current system, I've implemented threshold values for acceleration and tension in order to detect a spike in each. In my experience, this has worked reliably well, although in the future I may also implement wedge breaking detection through monitoring the length of the cables and possibly using computer vision. Once the wedge is broken, we must correct the rotational misalignment between the peg and the hole. This is accomplished by utilizing the onboard IMU to measure the tilt and to coordinate the lengths of the cables to adjust the tilt. After the tilt is corrected, we reinsert the peg. This process can be repeated if the peg were to repeatedly experience wedging. Using the 3D Winchbot prototype, I conducted experiments to verify the wedge correction strategy I just described. In the graph on the left, the top graph represents the tension in each cable, and you will notice that when the peg becomes wedged, the tension in the cable simultaneously goes to 0. You also see a subsequent spike in tension as the wedge is broken. After the peg is reinserted, the jam-free control strategy is implemented, leading to successful insertion. The second plot is the peg depth. You can notice the slight movement of the peg as the wedge is broken and as the peg tilt is adjusted. And you'll also notice the smooth reinsertion. The third graph represents the jamming inequality, highlighting the successful reinsertion of the peg. And finally, the fourth graph represents the tilt in black and the peg acceleration in red. During the chamfer crossing, the tilt of the peg is quite large. You can also plainly see a spike in acceleration as the wedge is broken. Then the tilt of the peg is visibly reduced to be about half a degree in both roll and pitch. These experiments verify the wedge correction strategy implemented on the Winchbot controller. So in summary, using the Winchbot system, we're able to perform precision assembly of a heavy shaft into a hole with minimal clearance. This has been accomplished through my work in which I derived the necessary conditions for the peg to cross the chamfer, enter the hole successfully, and obtain full insertion by avoiding jamming and correcting for wedging should it occur. I've experimentally proven the validity of this work and believe that it could be implemented in a factory setting. Thank you to Professor Asada and my committee for all of your support and guidance. Thank you to all of my lab mates, especially Cormac and Ice-K, for all of their help and for being endless sounding boards. I'd also like to thank my family, particularly my parents and my husband, for supporting me and encouraging me throughout my education and graduate career. And I'd finally like to thank all of my wonderful friends without whom graduate school would not have nearly been as much fun.